Hey everyone, welcome to another session of CeerazzleDazzle Physics. In today's session, guys, we're going to be doing a whole video on total internal reflection. And before we get going, make sure you hit the like and subscribe button to keep my channel going and keep my content as free as possible. If you get stuck with anything that I'm explaining, guys, just comment below and I'll do my best to answer your queries. Alright, so let's get straight into it. Okay, so over here I've got three semicircular glass blocks. So here it's a glass. This one is made out of glass. They're all made out of glass here. What we're going to be doing is we're going to be shining a ray of light going inwards through the glass, and we're going to see what happens to it as it exits the glass. So glass over here, and this medium over here is going to be air. First of all, we know that, okay, so let's say the light comes in over here, hitting it over there. We know that refraction will take place. And look, it's now bent away from the normal. The reason why, I'm going from more dense to less dense. Yes, hence why it moves away from the normal over here. A common question I get asked is, why is there no refraction over here? It's because it hits it at 90 degrees and therefore there is no refraction occurring over here. And that's the reason why I've used a semicircular glass block. Right, so the ray of light travels, hits it, and then moves away. Okay, so going from glass into air. Right, so let's remember Snell's law. We know that n1 sine theta 1 is equal to n2 sine of the angle theta 2. Right, that's Snell's law. If you're struggling with this, watch my video in the chat and you should be able to see it. n1 sine theta 1 is equal to n2 sine theta 2. I walk you through how to use that formula. We know that, we're going to label it actually. Let's label theta 1 over here. This one is theta 1 over here. And this one is theta 2. Don't forget, it's the angle from the normal out and the normal out on the top here. Right, so n1 is going to be this medium because I'm going through here into this one. So n1 and this one will be n2 over here. Right, so the first thing to notice is that as we're going from glass into air, we're going from more dense to less dense, and the refractive index of the first medium, which is the glass, refractive index of glass is going to be greater than the refractive index of the air in this case, or n1 is greater than n2. If you don't understand the concept of refractive index, there's another video in the chat, just watch that and I'll explain it for you. Right, so now from here what we're going to do is we're going to increase the angle of incidence over here, and we're going to see what happens to the angle of refraction as it comes out. Right, so as we increase the angle of incidence, we will notice that there's a point that it hits here and the ray of light will go along the boundary here. This angle of incidence, this is known as the critical angle. We're going to label it C. So let's put that down over here. C is equal to the critical angle over here. Very good. Right, now labeling theta 2. So what is theta 2 now? Theta 2, don't forget, it's normal out. It's 90 degrees here. So the critical angle is going to be the angle of incidence at which the refracted angle is 90 degrees. So let's put that down over here. When theta 1, don't forget, when this angle is equal to the critical angle C, we are going to get theta 2 going to be equal to 90 degrees over here. Alright, you're probably thinking where on earth we're going with this. Well, just follow with me and then we'll discuss it afterwards. We're going to go beyond the critical angle. So let's say we chose an angle greater than the critical angle. Let's say it's over here. We will notice that the ray of light will not even go along the boundary. It will be reflected inwards over here. And so obviously this angle right now over here, this is theta 1 again. So right now, if theta 1 is going to be greater than the critical angle, which was over here, we notice that the ray of light is going to be reflected inwards. So yes, it's perfect reflection within the glass itself. Therefore, we are going to call this total internal reflection. Why? There's reflection, it's internal within the glass, and all of it's going to be reflected. Hence why it's called total internal reflection. So theta 1 is greater than critical angle, total internal reflection occurs. Reflection occurs. Okay, excellent stuff over here. Okay, so now from here, guys, you're probably thinking, hang on a minute, what is the use of this? Why would I ever want to use this? When is this going to be useful for me? Well, what about the following? Okay, so here is a wonderful simulation which I'm going to use to explain the use of total internal reflection. I've put the link in the chat, you can click on it if you want to. Right, so over here we have our semicircular glass block, and look, the ray of light, C, Because the angle of incidence is greater than the critical angle, it's getting reflected internally. Then what happens if I was to put another piece of glass over here? What do we notice? Look, over there, looking over here, look, and there we go. We can keep reflecting the light wave again and again. So there we go. So look, it gets reflected again and again here. This is going to be the physics behind optical fibers. So when you actually see optical fibers, and this is how they're sending data at such a rapid rate, it's because they have glass fibers and the wave is being bounced along the inside of it via total internal reflection. Obviously, the angle which they're sending it off at must be greater than the critical angle, as we just looked at before. Alright, so that's a good use of total internal reflection. Let's go back and do some of the mathematics. Okay, right, so hopefully you remember that Snell's law, n1 sine of the angle theta 1 is equal to n2 sine of the angle theta 2. Right, now we're going to use it for this, the second diagram over here. So we know that, let's put it over here, so n1 sine of the angle theta 1 is equal to n2 sine of the angle theta 2. Right, theta 1 is obviously the critical angle in this case. n1 is obviously the first medium, n2 is going to be the second medium. We also know that the refractive index of the first medium must be greater than the refractive index of the second medium. So we're going to leave that as n1 over here. Then we're going to do sine of the angle C, yes. Then n2 is over there. n2, we'll leave it as that. And then sine of the angle and theta 2 now, this angle over here, theta 2, is 90 degrees over here. There we go. Right, n2 is obviously going to be equal to the refractive index of air, which is going to be 1.004. All right, so for this bit, I'm just going to approximate that to be equal to 1 right now. So n2 is going to be the refractive index of air, which is going to be 1. Okay, now from here, guys, sine 90 is what? That's going to be 1. So sine 90 is 1. n2, we said that's the refractive index of air over here. That's going to be 1 as well. So 1 times 1 on this right-hand side. n1 is going to be the refractive index of the first medium times by sine of the angle C. Then I can rearrange this. The refractive index of the first medium, or the glass, will be given by 1 divided by sine of the critical angle over here. So let's just put that into a nice box over here. So the refractive index of the glass can be worked out by 1 divided by sine of the critical angle over here. Make sure you can spot that yourself, and you can work from the Snell's law formula to get to this point over here, obviously by using the data we have over here. Okay, so from here we're going to tie in the concept of total internal reflection to optical fibers. Okay, so optical fibers, guys. So they're made out of glass, and around the glass they actually have a material called cladding. So this material over here, this is called the cladding. Yes, and obviously this is the glass over here. And total internal reflection is going to occur because you can send out signals, and look, as long as the angle over here, this angle over here, is greater than the critical angle, it will be reflected inwards again and again and again. As you can see, total internal reflection is the physics behind how optical fibers work. And don't forget, glass must have a higher refractive index than the cladding. So yes, the refractive index of the glass must be greater than the refractive index of the cladding for this to occur. So make sure that you're happy with that in terms of the refractive index. Alright, now from here we're going to move on to a couple of questions looking at total internal reflection and the critical angle. Okay, so here's a question. Calculate the critical angle of an optical fiber without cladding if the glass has a refractive index of 1.56. Okay, so I like to draw it, so let's just draw it over here. This is obviously the glass, and without the cladding it's going to be air. Instead of cladding, guys, there's just going to be air over here. We know that the ray of light will travel, hit it, and because I want to work at the critical angle, I know it will be along the boundary. So there we go, it's going down over here. This is going to be the critical angle C over here. Now from here, let's do this then. So if you want to work at the critical angle, we know that n1 sine of the angle theta 1 is equal to n2 sine of the angle theta 2. Right, n1, the refractive index of the glass, which is given to us by 1.56. 1.56 times by sine of the critical angle, which is going to be C, is equal to the refractive index of the second material, refractive index of air, and I'm going to take that as 1 for now. Yes, so we're going to take in the refractive index of the air is equal to 1. I know it's equal to, approximately equal to 1. I know it's actually equal to 1.004, but just for this question, we're going to take it as 1 over here. So 1 times by sine of theta 2. theta 2 is going to be 90 degrees, which is therefore going to be equal to 1. So therefore, rearranging this, then we know that sine of the angle C is equal to 1 times by 1 is 1. So 1 divided by 1.56. And therefore, C is equal to sine inverse, open bracket, 1 divided by 1.56 over here. So there we go. What we're going to get, I'm going to get the answer of C going to be equal to 39.87 degrees. So that's going to be my critical angle over here. 39.87 degrees. Then next question. When the cladding is added of refractive index 1.49. Okay, so let's draw it again. So now we have the cladding. It's going to be the cladding around the glass. So obviously my glass is over here. And we know that the ray of light, we still want to work out the critical angle. So we know it's going to be traveling along the boundary. And the critical angle is here. The refractive index of the cladding is going to be 1.49. So this one is obviously N1. We said the glass was 1.56. N2 in this example over here is 1.49. And look, we can see that the cladding has a lower refractive index than the glass over here. Then we can now plug them into the formula. N1 sine of the angle theta 1 is equal to N2 sine of the angle theta 2. N1 is 1.56 times by sine of the critical angle C is equal to N2 1.49 times by sine of the angle theta 2, which is 90 degrees once again. So therefore we are rearranging this then, so it becomes sine of C is equal to 1.49 divided by 1.56, and therefore C is equal to sine inverse, open bracket, 1.49 divided by 1.56 over here. I'm going to get the answer for the critical angle right now with the cladding, 72.77 degrees over here. So look guys, as you can see, if you have air surrounding your glass, the critical angle is lower, yes? But if you have cladding, the critical angle is going to be higher, 72 degrees over here. Wonderful stuff. And that's it guys for another session of CeerazzleDazzle Physics. Make sure you hit the like and subscribe button to keep my channel going. If you don't understand anything, just comment below and I'll do my best to answer you. Take care guys, goodbye, ciao ciao.